Thank you for watching this video. So this video will be doing question 3 of November 2021 question paper physical sciences paper 1. And this is the vertical projectile motion. So I'll read the statement and then answer the questions that follow. So let's go. A hot air balloon is moving upwards at a constant unknown speed. Right? So they're telling you that you have this hot air balloon, right? And this hot air balloon of yours is moving upward, right, at a constant unknown speed. That's what they're telling you. This thing is moving at a constant unknown speed. No problem. So 3.1, is the hot air balloon in free fall? Choose from yes or no. Give a reason for your answer. So they're asking if this hot air balloon of yours is in free fall. So they want you to say yes or no, and then explain why you chose whatever answer that you chose. No problem. First thing, what does it mean to be in free fall? That's what I think we need to understand first, to be in free fall. So, when an object is in free fall, it means that free fall is the type of motion in which the only force influencing that motion is the gravitational force. So, if you're saying an object is in free fall, you are saying that the motion of that object in question or our object of interest is influenced by gravity only. So it's the only force that is influencing that motion. That's what you say. So free fall is the type of motion that is influenced by the gravitational force. So, very important. So, gravity should be the only force influencing that motion. That's what free fall is, right? And we know that if gravity is influencing our motion, we know that the gravitational acceleration of that motion, G, is equal to 9.8 meters per second towards the center of the Earth. Right? So, we know that the gravitational acceleration of a free-falling object or a free-falling body is 9.8 meters per second. This is the magnitude of the acceleration towards the center of the Earth. This will be acceleration of your motion. Right? No problem. So, here we're told that this hot air balloon of ours is moving upwards at a constant unknown speed. Right? No problem. So, they wanted to decide if this thing is free falling or not. So now, is this thing free falling? So how do you decide that? You first check that is this motion only influenced by gravity only? That's the question that you should ask yourself. But this object is moving upward. Is that the influence of gravity? This thing is going upwards. Is gravity responsible for that? Is gravity the one causing this thing to move upwards? Then if yes, gravity is the one pushing that thing to go upwards, then yeah, it is free fall. But we know that gravity will pull this thing downwards towards the center of the Earth. That's how we know the behavior of gravity. We know gravity behaves in that manner. It should be pulling this thing downwards. The fact that this thing is not being pulled downwards, it's moving upwards, then there are other forces involved. So this thing cannot be in free fall. The second thing that you can also look at, the velocity of this thing is unknown, right? But we know that it's going upwards at a constant speed. So this thing have no acceleration. The acceleration is 0. Because the velocity of this thing does not change. Because the velocity is the magnitude plus direction. So we know there is the magnitude at which this thing is going upward. And it's going upward. So we have the velocity of this thing. The velocity of this thing is constant. We know, okay, we don't have the actual value, the numerical value, or the absolute value. But what we know is, we know that there is motion, an upward constant motion. So we know that the velocity of this thing is upwards and is constant. Right? So, from that constant velocity of yours, you can, if the velocity is constant, that means the acceleration is 0. Right? Because you know that acceleration is the rate of change in velocity, which means, in simple terms, the measure of how much velocity changes per second. But if the velocity is constant, there's no change in velocity, which means acceleration is 0. Okay, now, to answer our question, let's read it again. Is the hot air balloon in free fall? Choose from yes or no. So, the answer is no. The hot air balloon is not in free fall. Why do we say that? We can say there are other forces that are responsible for the upward motion. Right? Which means we don't only have gravity there. There are other forces that are responsible for this thing to go upwards. Right? We can also add and say, and acceleration is equal to 0 meters per second. Right? Because if this thing is moving up at a constant velocity, then acceleration is 0. Because acceleration is the rate of change in velocity. In simple terms, you can say it's a measure of how much velocity changes per second. But we know that velocity is constant, right? So our acceleration should be 0. But for free-falling objects, your acceleration should be what? 9.8 meters per second towards the center of the Earth. That's it. So, if they're asking on their question that if this thing is free falling or in free fall, we say no. There are other forces that are responsible for the upward motion of this thing. And our acceleration is 0. But for free falling object, acceleration should be this, towards the center of the Earth. So this thing is not in free fall. Done. We move to the next one. So we go to 3.2, I think, or maybe, yeah, 3.2. What are they saying at 3.2? Let's read. They are saying when the balloon is 200 meters above the ground, a small stone is dropped from the balloon. Right? See the diagram above. Another small stone B is dropped 5 seconds later from the balloon while still moving upwards at a constant velocity. Stone A strikes the ground at 62.68 meters per second. Ignore air resistance. Let's read this thing again. They're saying that when the ball is 200 meters above the ground, a small stone called A is dropped from the balloon. See the diagram. Another small stone B is dropped 5 seconds later from the balloon while still moving upwards at a constant velocity. No problem. What are they saying? They are saying here, when this air balloon of ours is 200 meters from the ground, a stone called A, I don't like it, a stone called A, let's draw it here. Here is a stone. It's called A, it's okay, it's very far, you know. Let me fix this diagram. So here is our stone. Our stone is black here. So they are saying when this hot air balloon is 200 meters above the ground, this is the ground, right? I can even make it rough so that it can be visible. So here's our ground. No problem. So when our hot air balloon is 200 meters above the ground, a stone A is dropped from the hot air balloon, right? And 5 seconds later, which means after some time, after 5 seconds, so this one is dropped, right? And then it continues going upwards, this hot air balloon of yours. Let me make it black. So here is a hot air balloon. So here is your hot air balloon. 5 seconds later, it's up there after 5 seconds. So from here, where it is here at 200 meters to there, actually, let me write, this is 5 seconds later. Another stone B, another small stone B, here is it. It's dropped from this thing. So here is your hot air balloon. So let me just try to explain this again. So they are saying now, when this hot air balloon of yours is 200 meters above the ground, right? A small stone A is dropped from the hot air balloon. And then it moved up for 5 seconds. After 5 seconds, another stone, which is B, was also dropped from this thing, which is from the hot air balloon, but now at a higher position, because if it continues going up at a constant velocity, right, then after 5 seconds, it will be a bit higher than where it was when A was dropped. It will be up here. That's what will happen. So this is where the first stone is dropped. This is 5 seconds from here to there. Here's your 5 seconds. And then now another stone is dropped, right? So what they're saying now, when B was also dropped, it was still moving at this constant velocity, right? And they're telling you that this stone A, which is this one here, it did hit the ground. It did hit the ground at a velocity. So it did hit the ground at a velocity of what? Of 62.68 meters per second. So the most important part is understanding this. Once you understand this, then everything else will be fine. So this guy is dropped 200 meters above the ground. And then now, 5 seconds later, another ball is dropped. Another ball is dropped 5 seconds later. So now, we're told that ball A did reach the ground at this velocity. That's what they told us. Does make sense. So they're saying ignore the effects of air resistance, which means there are no other external forces influencing this motion. So this motion is now in free fall, which means the motion of the balls, not of the hot air balloon. No problem. So let's go. For going to 3.2, they are saying calculate the speed of the hot air balloon. So they want us to calculate the speed of the hot air balloon. Okay, how do we do this? So, you know that if you are in a car, right, and the car is moving at 100 kilometers per hour, relative to the ground. You are also moving at 100 kilometers per hour because you're inside the car. So you're moving at the same velocity as the car. So when the car stops, let's say the apply brakes, you continue going forward. The reason you continue going forward is because of your initial, you are maintaining that 100. You want to continue in a straight line with that speed of yours, with the same 100 kilometers per hour, right? Which means if you move at 100 kilometers per hour and someone apply brakes, you will continue going forward before you stop. The reason you continue going forward is because of the inertia of your body. So you want to maintain that same speed. So when the stone is also dropped there, one would think if I hold this pen like this and drop it, the initial velocity of this pen of mine is 0 here. If I drop it, it falls down and start gaining velocity, right? Because here it's 0. So if we go back to this situation, this ball, this hot air balloon is moving upwards, which means the ball, before it was dropped, it was because it was held by someone inside this hot air balloon, moving at the same velocity as the hot air balloon. The ball was also moving at the same speed. So if you let go of that ball, it will not just go straight down. It will first try to maintain its continue upwards with this initial velocity, which is the same as that of the hot air balloon. And of course, due to gravity, its velocity will diminish, going up until it gets to 0 and then drops down. So if you think about it, this ball here of yours, ball A, will continue going up a bit with the same speed as this one. So this ball, the velocity of the ball will be that of the hot air balloon. That's what I'm trying to say. The velocity of the ball will be that of the hot air balloon, because it will continue moving up because of its inertia. That's what I wanted you to understand. So I would not want to think it will behave like this pen. This pen here has the velocity of 0 from the beginning. So if I let go of it, its initial velocity is 0. But if I was moving upwards at 2 meters per second, and then I drop it while I'm moving up at 2 meters per second, its initial velocity will be 2 meters per second upwards. That will be its initial velocity. So the ball had the same velocity. The ball had the same velocity as the hot air balloon at the beginning. That's what you need to know. No problem. What else do you do? So when I deal with these things, where my motion starts, I treat this area as a 0 reference. So I will take up to be positive. All vectors, all upwards vectors, I take them as positive. All vectors downwards, I take them as negative. No problem. So now, which means this line of mine, I'm taking it as a 0 reference, which means all my delta x, all my displacement above this point will be positive, and all displacements below this point will be negative. Right? Let me say delta y. All displacements above this point, I take them to be positive, and all displacements below these points, I take them to be negative. And all velocities going upwards, I take them to be positive, and all velocities that are going downwards. Actually, let me not do this here. So at this point, all velocities that are going up are positive, and all velocities that are going down are negative. So the initial velocity of this ball should be positive, because this ball will first go up with the initial velocity that is the same as that of the hot air balloon, right? And then eventually it will come down. So its initial velocity, I expect it to be positive, and this final velocity, I expect it to be, it is negative because it is downwards, because it's you can see it, it's this line here. This is the final velocity, This is the final velocity of ball A. It should be negative because it's downwards. All vectors pointing downwards are negative. That's what this thing means. All my vectors that are pointing downwards are negative. All vectors that are pointing upward are positive. And all displacements above this point are positive. And all displacements below this point will be negative. So now, they wanted us to do what? They wanted us to calculate the speed of this thing. Right? So what do we know? We know the displacement of the ball. The displacement of the ball, which means is the change. Displacement is a change in position. So the ball was dropped here, right? So the change in position, it is the final position minus the initial position, right? So the initial position is here, which is what? Which is this point that I've taken this as a zero reference. So this is my initial position, right? This is the final position. So the displacement, here is it. The displacement is the change in position, is this distance here, which is what? Which is 200 meters. But because it's below my zero reference point, it's going to be negative because it's below my zero reference point. It's going to be negative because it's below my zero reference point. So I said that all displacements above this line are positive and all displacements below this line are negative. So we know that our ball, its displacement is negative 200 meters because from here to here is negative 200 meters. From its starting position to where it is, to where it ended, is 200 meters. So your displacement is what? Is negative 200 meters. What else are you given? You are given the final velocity of the ball. What is the final velocity of the ball? The final velocity of the ball is what? The velocity at which our ball hit the ground, which is minus 62.68 meters per second. It's negative because it's going downwards. It was a downward velocity. This one is below our starting point. So, what else are we given? Nothing much. So what we want the initial velocity. This is what we want. So you know your equations of motion. There's one that says Vf squared is equal to Vi squared plus 2g delta y. There's one like this. So you have the final velocity. You want the initial. You have gravitational acceleration. Your gravitational acceleration, is it upwards or downwards? The gravitational acceleration is downwards. So it is negative because we said all vectors downwards should be negative. So your gravitational acceleration should be negative 9.8 meters per second. So what is your final velocity? It's minus 62.68 or squared. It's called Vi squared plus 2 into minus 9.8 times delta y, which is the displacement, which is minus 62.68. So you solve for your Vi. Now let's use our calculator. What do we do? Punch this. We say minus 62.68 all squared. So it's 3928.78 is equal to Vi squared plus punch whatever that is 2 times minus 9.8 times so this is a displacement, sorry. It should be a displacement here, which is minus 200. Because we said our displacement is minus 200 times the negative 200. So we have plus 3920. Then we transpose this to the side. What do we have? We have 3928.78 minus 3920, which is this, is equal to Vi squared. What is the difference with that? Say this minus 3920. this minus 3920. The answer is 8.78 is equal to the I squared. V plus or minus. So your initial velocity is equal to 2.96 plus or minus 2.96 meters per second, right? And now the question becomes, is it negative or positive? So now to decide that, we come back here. When the ball was dropped, it had the same velocity as the hot air balloon. The hot air balloon is upward, so the initial velocity of the ball is upward as well. So it went up before reaching its maximum height and then went straight to the ground, right? So it makes sense for this thing to be positive, right? This is the speed that they want, but if you want to make it a velocity, you can just say upwards. So the speed of this thing is positive 2.96 meters per second. And the velocity, you can say positive, you can say 9.6 meters per second upwards. That would be the velocity. So they only wanted the speed, so I can leave it there. Right? No problem. So we move to 3.2.2. What are they saying? They're saying, calculate the time it takes for stone A to reach the ground. So, here is our stone A. So, it was released here, and here is its own motion to the ground. It goes to the ground there. So, they want the time it took. They want the time it took for our stone to do all this motion. Right? So, we know that the gravitational acceleration is minus 9.8 meters per second. It's negative because we said all motion downwards is negative, or all vectors downwards are negative. So we had the initial velocity to be 2.96 meters per second upwards, right? And we had the final velocity to be minus 62.68 meters per second. So now what we want the time. So the question that we'll ask ourselves now is, how long did it take our ball to change from this velocity to that velocity? That's the question that we're asking ourselves. How long did it take our ball to change the velocity from this to that? Because that's what they are asking. Because they're asking how long it takes for the ball to reach the ground after being released there. What we know is that its initial velocity was that, and its final velocity was that one over there. So we want to know, how long did it take our ball to change its velocity from that initial one to that final one at the bottom. Then that will give you all the time it took to reach the ground. So, what do? We say, okay, one of our equations of motion, you can say Vf is equal to Vi plus G delta T, right? What is your final velocity? It's minus 62.68. It's equal to Vi, which is the initial velocity, which is 2.96 plus negative 9.8 delta T. So, now we solve for our time. So what do? We transpose this to the side. So we have minus 62.68 plus 2, or minus 2.96 equal to minus 9.8 delta T. So punch this. Say minus 62.68 minus 2.96 is equal to minus 65.64 is equal to negative 9.8 delta T. So divide by minus 9.8, divide by minus 9.8. So your time is equal to the answer to this. So divide by minus 9.8. So the time is equal to 6.70 seconds. So our ball from here, from being released here, it went up get the maximum point, and got all to the ground. So it took 6.70 seconds to reach the ground. That is the time it took for the ball to reach the ground, which is our stone. I don't know why I'm calling it a ball, but it's our stone. I'm sorry for saying it's a ball. It is our stone. So our stone took 6.70 seconds from being released here up until it hits the ground. No problem. We're done with this. So we move to 3.2. We need to 3.2.2. So I'll clean the board so that we can do 3.2.2. So, but I don't want to lose all this information. So the initial velocity here of the ball, let me write all this information. So actually I'll write it down. Let me just clean the board, I'll write it after. Okay, so now I've cleaned the board. So here the information for stone A, the one that we've got so far. We discovered that, we calculated that the initial velocity of the stone is 2.96 meters per second, right? Upwards. And then now, the final velocity at which the stone hits the ground, it was given to be 62.68. And we also found that the stone A took 6.7 seconds to hit the ground. So we move now to 3.23. What are they saying? They are saying calculate the distance between the hot air balloon and stone B at the instant when stone A strikes the ground. Let me read this thing again. They are saying calculate the distance between the hot air balloon and stone B at the instant when stone A hits the ground. So they want you to find the distance between stone B and the hot air balloon, right? When this one was hitting the ground. That's what they wanted to find. So I'll try to draw this thing so that it makes sense, right? No problem. So let's say we have ground here. See, here's our ground. Let me make it like this. So let's say this is your 200 meters, right? This is your 200 meters. This is where everything started. Here, everything started here. And then now, we know that this stone B was released, was dropped after 5 seconds. It was dropped 5 seconds later. 5 seconds later. That's what we know. It was dropped 5 seconds later. This is what we're given. So now, what you need to understand. Okay, I'm worried that I might not have explained the question very well. So, what this question is asking you, they want you to find how far apart is the hot air balloon and the stone B at the time stone A was hitting the ground. That's what they want to find. They want to understand how far apart was the hot air balloon and stone B at the time stone A was hitting the ground. I hope it does make sense. So what I'm planning to do, my plan, I want to calculate, to find the height at which stone B was released. Right? I want to calculate the height at which stone B was released. I want to calculate that height at which stone B was released, which means I need to know what this displacement is. Right? After knowing this thing, I know this was 5 seconds. This was 5 seconds after stone A was released. Which means we know stone A took 6.7 seconds to hit the ground. That means at the instant when stone B is released, stone A was left with 1.7 seconds to hit the ground. Let me repeat this. What I'm saying is, stone A was released here, right? And then after 5 seconds, which is this displacement here, after 5 seconds, stone B was released. So, here's stone A, here's the motion of stone A. It took 6.70 seconds, the motion of stone A. It takes 6.70 seconds. And this one was released 5 seconds later. So if stone B here and A here, if stone B here is released 5 seconds later, at the time difference between stone A and the time difference between, okay, by the time after 5 seconds when B is going to be released, stone A is left with only 1.7 seconds because your time will be 6.70 minus 5 seconds. So this is the duration. Let me remove the units. This is the duration of stone A in motion. This one is the time difference between stone A and stone B being in motion together. So they are 5 seconds apart because stone B was set in motion after 5 seconds. So which means this one and this one will only be in motion at the same time for how long? For only 1.70 seconds, because when stone B is released, which is 5 seconds later, this one is only left with 1.70 seconds, because if you remove that, this 5 seconds of going up, this one is traveling that 5 seconds from that 6.70 seconds. So when this one is finally released 5 seconds later, this one, the ball is only left with 1.70 seconds. That's what this thing is saying. This one, when this one is released, stone A is left with 1.70 seconds before it hits the ground. So, what do? We say, okay, so we know that by the time ball A hits the ground, right, stone B will only be in motion for 1.7 seconds. For that tiny time there, because that's the only time that stone A and stone B will be in free fall. Because I said that if stone A takes 6.70 seconds to hit the ground and the other one is released 6 seconds later, by the time stone B is released, stone A is only left with 1.70 seconds. So what you need to know this 5 seconds to this point, from A to B, on that 5 seconds to that point, what is the displacement there, right? So what is this displacement? You need to know this displacement here. You need this displacement here for that 5 seconds, right? Once you know that displacement, then now you will calculate, because once you know that displacement there, right? Once you know that displacement, I'm not sure if you really need it, but once you know that displacement, then we can find how far apart will the hot air balloon and the stone be after 1.57 seconds. That's what we need to know. No problem. So what do we do? I don't think we will need it. I don't think we will need this. But just for safety, I'll do it. So what I'll say, okay, for that 5 seconds, let's find that displacement there. I'm not sure what I'm going to do with it. Displacement is equal to VI delta T plus half your acceleration delta T all squared. right? But we know from here to here, we want that displacement, right? We want that displacement. The hot air balloon and the stone B are moving at the same velocity, at that constant velocity that we were told there, right? So we know that from A to this point here, upper point there, from this point A to that upper point there, the stone and the hot air balloon are both moving at what? Are both moving at the same velocity, that constant velocity, because the stone is inside the hot air balloon. So if the hot air balloon is moving at a constant velocity, so is the stone. So now if that velocity is constant, what is the acceleration? It's 0. So this part is 0. So your displacement is equal to VI, which is what? Which is 2.96. That's the velocity of this. That's the velocity of the hot air balloon or the stone times delta T. How much time from here to there is 5 seconds plus half of your acceleration, which is 0, times 5 seconds all squared. So delta Y is equal to the answer of this thing, which is 2.96 times 5. So the displacement is 14.8 meters above where stone 8 was dropped. So from here, the change in position from here to there is what? Is 14.8 meters. This is the displacement, 14.8 meters. That's the displacement, which means the total height to this point is what? The whole height up to that point now is 200 plus that, which means the height there at that point, we can say this entire height is 214.8. So this is the height of the entire, from the ground up until the point where ball B was dropped. Right? No problem. So what do we do now? We say, okay, now, at this point now, which means 214.8 meters above the ground, stone B was dropped, which means stone B went up, right? And reached the maximum height and went down. That is what we know, right? But what we know is it went up, its motion only lasted for how long? It only lasted for 1.70 seconds. Its motion lasted for how long? Its motion lasted for 1.70 seconds. It lasted for 1.70 seconds. So we know that. So we can find the displacement of stone B. So this would be our zero reference for this motion. So we can find the displacement from this position of ball B, which means how far is ball B from its starting position. That's what we can find. That's what displacement is the change in position. So when after 1.5 seconds, how far is ball B from its starting position? That's what we need to find, right? So we can say, okay, delta Y is equal to VI delta T plus half G delta T all squared. This one is in free form, right? So your delta Y is equal to your VI, which is 2.96 times 1.70 plus half negative 9.8 times 1.70. So the answer that you'll get here will be the displacement of ball B or stone B, which means how far, which is above or below from its starting position. So the answer, the sign of the answer will tell us if stone A was still above the starting position or below the starting position. If it comes below, negative, it means it is below the starting position. So you punch that, 2.96 times 1.70 plus 0.5 times negative 9.8 times 1.70 all squared. So the displacement of ball B is negative 9.13 meters. It's negative, right? It's negative, which means after 1.70 seconds, ball B is only negative, is only 9.13 below this point. So it's 9.13 below this point. It have not reached this point. It have not even reached that. 9.13 is the position. This 9.13 is the position of the stone B from its starting position. Is how far the ball has moved from its starting position, which means ball B started here and went down. So after 1.70 seconds, ball B is here, which means the distance between ball B and where it started is what? Is 9.13 meters. So this is what this 9.1 meters mean. Negative means below where it started, which means from where it started to where it is, the distance is 9.13, or the displacement. Right? No problem. Then now, as this ball B was on its motion for that 1.70 seconds, what was happening to the hot air balloon? The hot air balloon was also still moving up at a constant velocity for the same duration for 1.70 seconds. So your hot air balloon was also moving up for the same duration for 1.70 seconds. This is where your hot air balloon was doing. This is what your hot air balloon was continuing its motion, its constant motion for 1.70. So as this one was in motion up and down up to where it is now, the hot air balloon was also going up. So now, if we want to find the distance between the hot air balloon and stone B, we need to also know how far is the hot air balloon from the starting position, from where the stone was dropped. Which means we should also calculate the position of the hot air balloon for that 1.70 seconds. So what we do, say delta Y is equal to VI delta T plus half of A delta T all squared. I said A, not G, because I use G for gravitational acceleration, right? A for general acceleration, because that air balloon is not in free fall. So its acceleration is not 9.8 meters per second as our free falling stones, because our stones are in free fall, both of them, but the hot air balloon is not. Our acceleration is 0. So the displacement of the hot air balloon delta Y is equal to VI 2.96 times 1.70 plus half of acceleration, which is 0, times 1.70 all squared. So all of this part is 0. Punch this. Your delta Y is equal to, punch that, what do you get? Say 2.96 times 1.70. So you get that the displacement of the stone is 5.03 meters. So which means it's positive because it's above the starting point, which means your hot air balloon, its displacement from the starting line, it was 5.03 meters per second. Right? It was 5, which means the stone have moved 5.03 meters from the starting point. So you have a situation like this. If they both started here, right? This stone, the hot air balloon moved 5.03 meters from the starting position, and the other one moved negative 9.13 meters from the starting position. So you want to know how far apart are they, right? So that's the distance. So the distance will be equal to 5.03 minus negative 9.13, which is, that would be the distance between them. So the distance which is 14 5.16 meters. This is the first way in which you can find it. Another way that you can find this displacement, what can you say? You can say, okay, I know the height here. The height is what? Is 214.8, the whole height up until this point here. The stone, the height of the stone, it will be this entire height, no, not this entire height, this height up to this point. Then you subtract that 9. Then you can get where the stone is sitting, the height of the stone. So the height of stone B is equal to what? It's going to be equal to 214.8 minus is because up to this point the entire height is 2.1.4 from the ground up until where this thing is chilling. So it will be to find the height of the stone, it will be 214.8 minus 9.13, which is the height dropped from that 2.1.4. So the height of the stone is equal to height of stone B equal to 214.8 minus 9.13, which is the height of the stone was 205.67 meters, which means our height had not even reached that 200 mark. So it is still above this 200 mark that we were given initially. So now let's get the height of what? Of a hot air balloon. It's going to be what? The hot air balloon is here, which is going to be this 214 at this point, because from here to this 214 plus that height there. So the height of the hot air balloon is 214.8 plus 5.03, which is the height of the hot air balloon. 214.8 plus 5.03. So it's 219.83. So this is the height from the ground, right? Both of them, they are measured from the ground. So if you want the distance between them would be the height 219.83 minus 205.67. So your height, your distance between them is the answer to this, which is 14.16 meters. That is the distance between the two things, which is the same as that one. So the distance between this and this, is this, which is what is it? It's 14.16 meters. This is the distance that we're looking for. We're done with this question. So we have one more question. 3.3. So I'll clean this part. I think this part might be enough. This is 3.3. So what are they saying in 3.3? They are saying, on the same set of axes, draw the position time graph for both the hot air balloon and stone A from the moment the stone was dropped until it strikes the ground. Use the ground as zero reference. Label graphs for balloon and A. So they want a position time graph, right? No problem. So time, position in meters is your time in seconds. I don't even have the values. So what did they say? They are saying use ground as zero reference. No problem. So this was dropped at 200 meters. I don't think they even want this. This is 200. It went up, so this stone of yours went up and hit the ground, right? This is your A, this is your stone, this one. And then now, because it went up and down, So this is its motion over time, right? So this one was constant. It was moving at a constant speed. So the rate of change, so it was moving at a constant speed, right? So which means it was moving at a constant speed. So how do we show this? Show this on sort of a straight line like that. So this is your ball, this is your hot air balloon, this one. So it's constant motion. You can see it because it was rising at a constant rate. Because it's going up at a constant rate. That's what is happening. But I think I need to be more careful and say, because the ball strikes the ground there, right? You should extend this up until it hits that line, because this is where the ball hits the ground. So they should be stopping at the same time. So the hot air balloon will have this shape because the rate of change of the height was the same the whole time. So it was increasing, the height was increasing at the same rate. So this is how it looks like. So this is your hot air balloon and this is your stone. And we should be done. It was not a very fun question, this one. I hope it does make sense to you, as it does to me. If you like the video, let us know in the comment section. Like and subscribe for similar content. Until next time, Godspeed. Cheers.